Thank you, Netta. And thanks everyone for coming. It's great to see you all in person, and also nice to be back in Firenze. It's been a long time for me. Okay, so one of the key things that we learned over the last few decades is that in quantum gravity, space-time is emergent. Okay, and of course those are nice words to say. You know, what do they mean? Well, I don't know exactly, but something they mean, I would say, is that in the fundamental description of what's going on, say like in the dual CFT and ADS CFT, then the bulk spacetime, the gravitational spacetime, is not manifest when you look at the fundamental degrees of freedom. The fundamental degrees of freedom, for example, are living in some other dimensionality, and it's only in some situations and in some approximation that the gravitational spacetime, that we usually think of semi-classically is really there. So in ADS CFT, we've understood that better in the last 10 years or so through this idea of quantum error correction. So the idea is if we have some dual CFT, say we can split the boundary into regions, capital B bar, and then there will be some quantum extremal surface in the bulk, which splits the bulk into the entanglement wedge of B and the entanglement wedge of B bar. And then the key point is that there's some map which takes the bulk Hilbert space, which I'll just mutilate as a tensor product and not respond to complaints that it's not a tensor product. There's some map which we think of as being an approximate isometry. Okay. So we have this effective description in terms of low energy fields propagating on the space-time, and then there's this approximately isometric map that maps that into the fundamental degrees of freedom. And when we say that the space-time is emergent, one indication of that is that this map is just an isometry and not a unitary, okay? So there are states in the fundamental description which are not in the image of the map, and the way that we usually think about that, what do those states look like in the bulk point of view? Those are states where some piece of the bulk has been eaten by a black hole, and we no longer have this smooth description of the entire space-time in the vicinity of the vacuum, okay? So, so in this, right, in the statement that it's error correcting code is just this, well, first it's the statement that you have this isometry, but then moreover the isometry kind of is compatible with the local structure of things in the sense that observables that are in little b can be reconstructed on big B, and observables in little b bar can be restricted on big B bar, and moreover we have this quantum extremal surface formula, so there are various ways to write it, but one way that I like is if we want to compute the entropy of some state on big B, then we compute the expectation value of the area of this surface over 4G plus the entropy in the bulk in the entanglement wedge. Okay. So this is some mathematical structure that all hangs together, and I would say gives us a good understanding, or at least a skeleton of an understanding, of how the emergence of space-time works in ADS CFT when you don't have these big black holes around, okay? And so the question I want to talk about today is, what about the black hole interior, okay? So this picture is able to account for the emergence of space-time outside black holes, and that's fine, but what if we want to know also what's going on inside the black hole? How are we supposed to think about that in the fundamental description of what's going on? So let's first think about what we might want. So in this talk, I'm going to focus on evaporating black holes because I'm going to try to make contact with the information problem. So you can ask me about non-evaporating black holes later if you want. We have some things to say about those too. So here's an evaporating black hole. And I'll just kind of make a cartoon of it. So let's consider a Cauchy slice like this, which is sometimes called a nice slice. And then there will be some degrees of freedom out in the Hawking radiation. So this is some arbitrary division here you can think of as happening at 3M or 4M, or if you really want to be precise, you can make this an ADS black hole and this a non-gravitational bath. So if you're unsure, you can think about it that way. So there will be some radiation degrees of freedom out here, and then inside the black hole, there will be some right-moving modes and some left-moving modes. So this is a kind of caricature of the degrees of freedom on this slice. It's not really 100% correct for several reasons, right? Like one thing, there's some degrees of freedom outside the black hole that I'm just going to ignore because they're not so important. There are interactions between left and right movers, so the split is not really well defined. You have to worry about diffeomorphism and variance, so you don't really have local degrees of freedom here, things like that. But all this is second order stuff that I'm not going to think about today. I'm just going to, this picture is already enough to have Hawking's problem, and so if we can understand this picture, then I claim the rest of it is sort of superficial embellishment on top of that. Okay, so this is the bulk picture. This is analogous to this H little b tensor H little b bar in ADS CFT, okay? And now what we would like is some encoding map which maps this into the fundamental description of what's going on, which I'll take to consist of some black hole system you can think of as a strongly coupled, one sec, Raphael, quantum system. Sometimes it's called a quantum dot. And then it's coupled to this radiation system. And so I'm always going to work in the approximation where I can treat the radiation system out here as being part of the fundamental description. I don't have to worry about the fact that the radiation itself is holographically encoded into some holographic dual of flat space. So that's of course true, but we don't think that that's activated for talking about, you know, a diffuse cloud of photons far away from the black hole. Another way of saying it is that this encoding here from here into whatever is the fundamental description of flat space should be isometric. There shouldn't be anything too weird going on with the encoding of the Hawking radiation, so I'll just take it to be the identity. And so, sorry, one sec, Raphael, one more thing. So then this V is a map from the interior degrees of freedom to B, which is the set of black hole microstates. So you should think of the dimensionality of B as being of order e to the a over 4g. Okay, so now Raphael.
The big R and little r, can I think of them as the outside and inside Hawking partners?
Yeah, that's correct. So this little r are the modes that Hawking says are entangled with big R. Yeah.
Now, in your original picture with just ordinary ADS with maybe a few particles in it, I could have divided little b, right, into two subregions with another homology surface, right? And I could have worried about the degrees of freedom on either side of that surface that are entangled with each other in the vacuum state.
Do you mean this entanglement?
No, I don't.
Oh, entanglement within here.
I want you to draw another homology surface that divides little b into two halves.
You mean, sorry, something like that?
Yeah, exactly.
Okay, yeah, but this one is the quantum extremal surface,
I know.
right? We can draw another one.
Right.
Yeah.
Let me worry about that other one for a moment.
Yeah.
There are lots of degrees of freedom. This is a totally random choice, but there are lots of degrees of freedom that are on the right and left of that new line that you just drew, which are entangled with one another in the vacuum state.
Yeah.
And we don't usually try to include them in the map from little b to big B.
Yeah.
Why do you do that here?
Good, yeah, so the way I think about that is if I tried, so that's a question of what do we include in the code subspace, and in particular, do we include states where there's high energy stuff here because we disentangled the modes, right? So the reason we usually don't is because here that leads to a large energy if you do that, okay? That produces a state that's very energetic, okay? But here, if you disentangle these modes, as we've all painfully learned over the last 10 years, that doesn't change the energy very much at infinity.
But usually we just focus on a code subspace where we freeze them to be in the vacuum state. And in that case, we wouldn't have to worry about.
Well, yeah, but that's not the way I usually like to think about the code subspace in the first picture. Is I take all the states globally whose ADM energy is less than something, and that makes sure that nothing too crazy is going to be going on in the subspace. But for the black hole, in order to have Hawking's problem, I really want to be able to think about, how shall I say? I mean, I want to think about the states where these might not be entangled, right? I mean, because those are allowed energetically, at least in the effective description. You can disentangle these without paying an energetic price. And so if you want to address question, I mean, that's kind of the argument.
But if you allow that larger code subspace, then you don't, then the interior is not in the entanglement wedge, right?
Well, it may or may not be. It depends on how many of the modes.
Let's just say we make it.
No, I agree that it's more complicated. So we have a whole section in the paper where we're thinking about if you disrupt the entanglement a little bit, how much does that change reconstruction and so on, right? I mean, this whole thing with pythons and so on is about
My question is, why do we worry about non-isometric codes when once you figure out what the entanglement wedge is, it's always an isometry if you really restrict to the code subspace that gave you that.
No, but it's not going to be. It's not going to be an isometry. I mean, let me say it in another way. Well, okay. Let me say the next thing I was going to say because I think that'll address this complaint. Okay. So, so we could try. So we can try to have a map V from the effective field theory degrees of freedom on this slice into the fundamental description. So here this just maps it into the microstates, and then this map acts trivially on the radiation, because that's just sitting out there. It could be some non-gravitational, spin system or something. But then there's clearly a problem here, which is that this V, it can't be an isometry in general. And why not? Well, it's because if the black hole is old, then we can get into a situation where the dimensionality of effective field theory degrees of freedom on this slice is large compared to the entropy of the remaining black hole. And let me say to Raphael, actually, so now one comment is, so even if I kind of demand that these stay entangled in the usual way, just these L modes also grows, right, as the bridge gets longer. So this L you can think of as keeping track of all the things you could have thrown into the black hole.
I agree with
Yeah.
Raphael that if you have this dark entropy, then that's not in the entanglement wedge, so you don't expect it to be able to
Sorry, the entanglement wedge of what? No, but I'm trying to describe the whole system. So it is in the entanglement wedge of B union R. I'm trying to describe the whole system, right? So, well, yeah, but the full holographic map is this. Yeah. I took the V to have this form. Sorry, it's a little confusing. This could be called V, and then this is some sub piece of V or something. But the full holographic. Yeah, because, I mean, so there's a bigger map which is V tensor to the identity on the radiation. It's just that I want simple observables on the radiation to map to themselves in the fundamental description, because the radiation is just some spin system.
But we know that, for example, for an old evaporating black hole, the interior is mapped to the radiation.
Yeah, but that's going to happen here. I have not precluded that by putting the identity here. Because V is not an isometry, so when you act with V, it can teleport information from L and R into the radiation, and that's what happens. Yeah. Yeah.
Tell me if you agree with this. For a bag of gold situation, you have a non-isometric code from the interior to B. But for an old black hole, you have effectively maybe an isometry from the interior to B union R.
No, it's not an isometry even to B union R. No, because
Might be effectively an isometry.
Well, it depends what we mean by, I mean, the whole talk is going to be about that effectively, but there will be states in the Hilbert space of BR which are annihilated by V tensor IR. Sorry, I said it backwards. There'll be states in the Hilbert space of this, tensor, that, which are annihilated by that. Okay? So it can't be an isometry. Because remember, R is on this slice too, so adding R doesn't help you keep it from being an isometry, right? Because the V tensor I acts on little l, little r, big R, and sends it to big B, big R. So the dimensionality of big R just cancels, right? The non-isometry comes from this part of the map.
Daniel, do you agree that anytime it looks to you like a non-isometry, that's always because you're including degrees of freedom, which, if you included them in the code subspace, would actually make the entanglement wedge significantly smaller? And
No,
make
I
it
don't think so,
isometric?
because the entanglement wedge of B union R is everything. Because B union R is the whole system.
Did you conclude there was an isometry from this space to B union R?
So, no, this is not going to be an isometry.
I know that.
Yeah.
Isn't there an isometry from the whole interior?
No,
From, okay.
no. No, because there are states which are null, right? There are going to be states that are annihilated by the map. Yeah. No, which I think we should, the argument of this talk is going to be that we should embrace the null states, not that we should try to get rid of them. Let me say though, right, so if you'd asked me, I mean, of course, this is an old problem, right? I mean, this, I'm not claiming I discovered that there's more degrees of freedom on the nice slice than there are in the microstates, okay? This is something people knew for 30 years, okay? If you'd asked me 10 years ago, when I was thinking a lot about this picture, if you asked me about that, I would have said, well, you're just taking this slice too seriously. There shouldn't really be, in this regime, there shouldn't be this global picture of the space-time, okay? This, because of black hole complementarity, whatever that meant. This description shouldn't be real, and you shouldn't believe all this stuff over here, and so you shouldn't ask about this map. That's what I would have said 10 years ago, okay? But 3 years ago, from some friends in this room, I learned that there's a benefit in taking this picture seriously, including all the way down the slice, which is that you can use it to compute the page curve, okay? If you just say, okay, whatever you can complain about this picture, but I'm not going to listen, I'm just going to take the picture seriously and use it, and apply the QES formula to it, then I get a page curve for the radiation and for the black hole, which has all the properties that we want, okay? And so the lesson I learned from those calculations is that there's got to be at least some sense in which we can take this picture seriously, okay? And that's what I'm going to try to tell you today, is what the sense is. Okay, so here's a proposal. So the proposal is that V tensor IR is highly non-isometric, and in particular, there are many null states, where null states are just states in the effective description that are annihilated. Oh, I should introduce this terminology because I'm going to use it a lot. So this picture of what's going on we call the effective description. Where effective kind of means effective field theory or something like that. And in this picture we call the fundamental description. Okay. So there are many states in the effective description which are annihilated by the holographic map, these null states. But this cannot be detected by any sub-exponential. So here this means sub-exponential in the logarithm of B, so that's sub-exponential in the entropy of the black hole, observer. So in the effective description, there's this large set of states that are annihilated by the map, but they all have exponential complexity. Okay, and so it's not obvious, but I claim therefore that means that someone who's only measuring simple things cannot tell that the map is not isometric. That as far as a person who can only do simple things is concerned, the map is in isometry.
Can I ask you a question?
Yeah.
Should it be, is it obvious that it's not just partial isometry? And so, for example, is the norm of this operator going to be large, or is it just, does it just like a projector? Because a projector would have lots of
No,
null space.
yeah. So it's kind of, yeah. How shall I say? Yeah, in some sense, yes. There will be a subspace where the norm is very close to being preserved, and then there will be a subspace of null states where it's annihilated. That won't exactly be true, but it'll be approximately true.
But I'm trying to make the distinction. But in your case, will the norm of this operator be larger? The operator norm.
A V, yes. So there will be weird states whose norm are enhanced by a large factor by this operator. That's correct.
Okay,
Yeah,
but that's
those
not,
will also have exponential complexity, but there will be states like that.
But I guess that's not. You could just have a projector which has norm 1.
Yeah, that doesn't seem to be what works. Yeah. So I mean, this is just some words, right? So I mean, it sounds nice, but the main goal is not to say the words. The goal is to show you mathematically that this actually solves all your problems. So I'm going to be pretty explicit in this talk. I'm being philosophical now, but there's going to be real calculations in a sec. Okay. Yeah, and so indeed, with the mostly okay, this sounds good, but then what we actually do in the paper is give some explicit models where you can compute things and really see how this works. So claim is there exist models such that so one V tensor IR preserves overlaps of all sub-exponential states to exponential precision. So that's clearly the best we should ask for. We shouldn't ask for exact things, right? We should only ask for things up to exponentially small corrections in the black hole entropy, which is log B, and so that's all we're going to ask for.
Daniel?
Yeah.
You're focusing on the black hole interior, but is there a way to characterize more generally when this is relevant? Is this like about lunches, or is it, potential lunches? Is this about?
Yeah, can I say it's about the Busso bound?
You can say whatever you like.
Yeah, I think there should be some kind of holographic bound where, this is kind of violating some kind of holographic bound, at least in some vague sense, right? Of course, it's not violating the true bounds, but it's violating some naive bound, right? I think there should be some argument like whenever you violate naive bound X, then the map stops being isometric. I don't know, maybe Netta has some comment about
why
this.
doesn't it apply? Let me just follow up on that. Why doesn't it apply to the example that I tried to construct with you in the beginning, which would also, in quantum field theory, we can always say that there are a lot of degrees of freedom in some volume of space.
Yeah, so I think if you really wanted to play this game, I think what you would eventually find is that you would be constructing hyperbolic black holes.
Yeah.
Okay, and then this story would apply.
Which is why the energy argument that you gave, I think, doesn't really apply.
Well, it depends what energy you talk about, right? The global ADM energy does give you a nice sort of sanitized code subspace, okay? If you want to play this game and talk about hyperbolic black holes, then what you say is you somehow stop caring about the global ADM energy and you just use some Riddler.
Let me just start with B and nothing else.
Yeah, so I think you can try to play that game and you'll come up with something similar to this. It's just that it'll be uglier because this B will be infinite dimensional, right? Because the area of these black holes is infinite. So that will complicate things a little bit. But in particular, I won't necessarily be able to make arguments like ironclad arguments that it can't be an isometry, maybe. I'm not sure. I'd have to think about it. But yeah, I don't see why there shouldn't be some story like this for hyperbolic black holes. But I think there always have to be black holes there. We had some discussion about this. Yeah. We couldn't come up with a situation where there weren't black holes in the code subspace where you were asking where it was non-isometric. Yeah, maybe Netta can say.
Assuming cosmic saturation.
Assuming cosmic censorship, that's right, yes. Yes, thank you. Yeah.
The reason that I'm harping on this is that, I mean, I don't think it's uninteresting to cast the bulk to boundary map as a non-isometric map. But if we first figure out what the code if we decide on a code subspace and we figure out what the entanglement wedge is, then I think we don't need to do that, right? What you're really doing is you're sort of involving degrees of freedom that would reduce the entanglement wedge if you actually included them in the code subspace, but you are including them in the map.
Yeah, but the thing is, I want to have a framework where I can understand the calculation that Netta and Ahmed and Jeff and company did. Henry, if he's here, I don't know. And in order to understand that in a coding language, you need to include all these degrees of freedom in the calculation because you care about things like the entanglement between this, right? You want that. Do you want to view that as logical? Because that shows up in the QES calculation.
I mean, it's basically the map from the non-bold to the bold state, right?
From the what?
From the non-bold to the bold state in the notation that Ahmed and friends once introduced.
Well, I could never understand exactly what they were saying, but...
The semi-classical to the true state.
Well, I think that's what you can think of this as. Yeah, this effective and fundamental. Yeah.
Isn't this fairly explicit in the West Coast model? Where
Well, it is if you believe Euclidean gravity, but in this talk we're not going to believe Euclidean gravity. We're only going to compute things using Hilbert spaces. Yeah.
But I think that's just a helpful example, at least for me, because yeah, then you would just say that the states of the brain are like your h left times h right, and it's very explicit.
Yeah. I mean, again, the idea that it's non-isometric is not, like, we didn't come up with that, right? Like, that's, I think even back into the 90s on some level people were saying that, right? I mean, this idea that if you try to study this whole Hilbert space, it can't really all get mapped, right? Yeah, and indeed, there's some calculations in the sort of end of the world brain model, yeah, that are kind of consistent with that. Yeah, that's correct. Yeah. It's really the complexity is kind of, well, there's two new ingredients here. There's including complexity, and then there's the actual models where you can compute things. Yeah. Yeah, but that's using, so Euclidean gravity doesn't count from my point of view of computing things because I only want to compute entropies in the fundamental description using the definition of entropy. I don't want to compute them any other way. Yeah.
Why are you calling the West Coast model Euclidean gravity? I mean, you can have just the Lorentzian space-time with some boundary range. You have some degree description.
Yeah, but I'm not sure if there's a sort of there's a bulk Hilbert space calculation where you can see the non-orthogonality of the microstates. The only calculation I know where you see that involves including these wormholes in the calculation of the inner product, right? Yeah, but here I'm going to see it without doing that. I'm not saying it's wrong, right? It's just, I wanted to see everything very explicitly.
You're not seeing it in the geometry, you're seeing it in some models, right? They had some models.
Well, let's see what the calculations are that I actually do. I think that these are more clear than that because that uses a black box. I mean, to me, Euclidean gravity is a black box. So it gives you the right answer, I don't doubt that, but I want to have something where I understand everything that happens without having to use a black box. Yeah, there was another question? Okay. We'll see how far we get, but it's okay, I like discussions. Okay, so yeah, I was saying, right. So first there's this idea that you can preserve the overlaps of all sub-exponential states to exponential precision. We'll see that you can compute entropies, say of B or R, BR, etc., either in the fundamental description using the definition of entropy minus trace log rho, or in the effective description using QES. And they agree up to exponentially small corrections. Okay. So, and this is a thing which I would really say was not done in the previous models, having two different computations where you can compare them. Okay. You can also reconstruct sub-exponential observables. And I just want to emphasize that the reconstruction is state dependent in general, or state specific, or nonlinear. Those words are all used to talk about similar things, but unambiguous, okay, which is an improvement on some of the previous things. And they agree with the effective description.
Sorry, I really want to understand what you're doing. I don't understand the statement 2 about computing the entropy. Like, do you mean by that we can compute them using the CFD, or we can compute them using the QES?
Compute them, both. So I compute them using the CFT, and then I get the same answer that I would have.
How has that not been done before? I mean,
Because we can't, well, I can't compute them in n equals 4. I can compute them in these models, right? It's hard to compute things in strongly coupled quantum systems, so you need some weapon.
so you're just, okay, so I thought in the CFD you would make some generic argument about how I get the page curve.
No. I'm going to have models where I do calculations. Everything here I said I'm going to rigorously prove in the context of the models, and then I'm going to suggest that it's true also in situations where I can't prove it.
If it's not the CFD, what do you mean by the fundamental?
You're going to see. Just be patient. Well, I said models, right? So I'm going to tell you what this V is. I'm going to construct, say, using random unitaries or in some, I'll have some Pagian.
What does that have to do with the fundamental description? I mean, by that I would normally take that to mean ground gravity theory or something like a CFD.
Yeah. No, but I said model, right? It's something that should be analogous to taking n equals 4 and coupling it to a bath, okay? But I don't understand that well enough, so I'm going to do a toy model of that. You can think about it as like some tensor network or something. It's in the same spirit, some discrete model of quantum gravity, but where there are analogs of all these things, and you can see how they fit together. But I think this will make a lot more sense if you just wait until see the model. But I'm going to inflict one more high-level thing before we talk about the model, which is I want to talk for a sec about the information problem. Okay. So Hawking says that there are three things compatible. Okay. So the first is that the black hole entropy is finite. The second is unitary evolution, which for us I'll take to mean in the fundamental description. And three, that EFT near a black hole is valid. Okay, and Hawking says these are incompatible. Okay. But what I'm going to say is that if I make a small modification, which is I say EFT for sub-exponential observables, then actually they aren't. And depending how far we get into the talk, I'll be able to write down for you a model which simultaneously has all three of these things. And so there is no contradiction between them. Yeah, Bartek. Yeah, I think in some sense that's right, because if you do something exponentially complex in the bulk, it's going to be, you'll see non-local violations of the space-time. But it's very non-violent, right? Because you have to do an exponentially complicated thing to see it. So I think in that sense, most of us probably always believed in non-violent non-locality, right? We thought that if you do some very complex operations, then we do believe the space-time is emergent, right? So what's really the difference between saying emergent space-time and saying non-violent non-locality? You know, probably it's just a political distinction, right? Yeah. Okay, and so the claim is they aren't, and I'll show you a model. If I don't get to it in the talk, I'll show anyone who wants at some point. I'm here for a week and a half, or for a week, I guess. Okay, and so that's the plan, and now we'll talk about the models unless anyone has more high-level gripes / questions. Okay, so let's start talking about. Oh, I see. Okay, well, yeah, I could try to write bigger. Yeah. Okay, so I'll start with static models. By that I mean non-dynamical models, where we'll just imagine that we've picked some Cauchy slice, and we'll just talk about the holographic map on that slice. Okay, and then later in the talk, I'll try to describe a model where we know how to evolve the map from slice to slice and interpret it in terms of unitary evolution on the boundary. So for the first part of the talk, we're only going to have 1 and 3 here. We're not going to have 2. And then we'll put in 2 later, okay? So here's our workhorse, the workhorse model. So what do I need? I need to tell you a V. Okay, so here's a V. So I have a Haar random unitary, which eats little l and little r, which if you want to, you can just think of as being a bunch of qubits or qdits or something. And then I'll also allow some additional degrees of freedom that are in some fixed state. If you want to give that fixed state an interpretation, you could think of it as, say, the stuff just outside the black hole, or just some degrees of freedom that we're choosing not to vary, similar to the discussion I had with Raphael about that picture. Okay. Then out of the unitary is going to come the black hole microstates, but then I'm going to do something sacrilegious, which is I'm going to post-select on some degrees of freedom p, and then it will turn out to be a good idea, as we'll see in a minute, to multiply by the square root of the dimensionality of p, okay? And so, Tom, this is what makes the operator norm big, yeah. So you can see that unless p is one-dimensional, this is not an isometry, right, because of this projection. Yeah?
Should I think of this addition?
Think of,
Should I think of this additional interval as something just small that you ask for we kind of to cover
this one?
additional things, or is this be substantial in the sense that its dimension will be comparable?
Yeah, you don't. It turns out you don't want the dimensionality of this to be too small.
So it even has to be large.
Yeah, you want it to be large. Yeah. Yeah, but for now, but it's also kind of just to give you a knob to turn in terms of, I'd like to vary B and P independently, and so in order to do that, I need to vary something down here, because this is a unitary.
So you need to fill out this.
I need to fill out the, yeah, yeah. Okay, so this is, oh, sorry. So if LR is much less than B, then I won't prove it for you now, but this is actually approximately isometric. And there I mean really in the operator norm, in the sense that you know, V dagger V minus the identity is much less than 1. Okay, so that's what it means to be an approximate isometry. This is in the infinity norm. So that's true if you're in the regime where L and R is small, and then the post-selection is kind of irrelevant, right? Like, yeah, there's some post-selection, but it's in some weird basis and doesn't really do much. You know, it shrinks the norm, but then this puts the norm back, and so then everything is good.
Can I, that's kind of like how random tensor networks work? Is
Sorry,
that right?
what?
Is that kind of like how random tensor networks work? They're approximately isometric.
Yeah, I think you can think of like that,
I
yeah.
think you also have to put a P there too. So.
Yeah, you have to put there's something analogous to this P that you have to put there. Yeah, the tensor network people are always very careless about these factors. They like to bend the legs around every which way without keeping track of the normalization, which is a source of great pain for anyone trying to understand what's going on. But yeah, if you do that right, then you'll get some factor like this. Yeah, maybe. I'm not sure. I'm not sure there's a hard random unitary in the West.
They have random vectors, which effectively is the same. Yeah. They have a bunch of random vectors, right? In a particular energy window, they're just completely Gaussian random vectors. And
Yeah, I thought maybe you mean there's different versions of the model. And the version of the model that I understand, it's the one where you draw pictures with these dots.
yeah, but you can take the output of the model. I mean,
Oh, just interpret the out. Yeah, you try to interpret the output like this. Yeah, that I think I agree with. Yeah.
I think if you take as a starting definition
Yeah.
the dual model that they proved is equivalent, then
Yeah. Well, I'm not sure if I'm not totally sure if they have these right moving modes though, right? Like I think the end of the world brain is kind of like L.
well, I would say it's L times R.
I'm not. Yeah, well, I thought, because it's supposed to keep track of the microstate. So the thing that keeps track of how you made the black hole here is L. Yeah. Yeah, but I mean, maybe, I don't know. Yeah. Yeah, I think if you try to interpret the output, maybe, I don't know. I'd have to think about it, I'm not sure. I feel like this is more precise than that, though, because anything which is based on calculations like this is going to be approximate. So this is an approximate isometry if L and R are smaller than B. But if L, R are big compared to B, then there's going to have to be null states just purely on dimensional grounds, okay? And so it's going to be very non-isometric. Okay, so let's just see a few, let's just and I should say just philosophically, let me say that although this U is random, the idea is you pick a U and you stick with it, okay? I'm not one of these crazy people who thinks there's fundamental averaging, okay? You pick a U and you stick with it. So I'll do averaging and calculations, but that's just to understand the features of a typical U. I don't think that there's actually averaging. Okay. So let me just quickly describe a few calculations. So one thing we can do is we can just pick two states. So let me write maybe over here, psi and phi are elements of H little l tensor H little r tensor H big R. So these are states in the effective description. Okay, and this is just on the nose equal to the inner product between psi and phi. So on average, any particular two states in the effective description will have an inner product which is equal to their sort of pre-inner inner product before we acted with the map. Okay. Now, in and of itself, that's not so impressive because the fluctuations could be large, right? And I just gave that whole rant about how we want to pick a U, okay? And so we should check the fluctuations. So, so we can just take this, the difference of these two things, okay? With a little bit of effort, you can show this is upper bounded by 2 over dimensionality of B, okay? So in other words, there are fluctuations, right, which reflects the fact that V is not really an isometry, but the fluctuations are exponentially small in the black hole entropy. Okay, so let me just, so I don't know, maybe depending on how much you thought about these things, it may be a little surprising that, you know, we could be in the regime where this is much bigger than that, so there are many, many, many null states, and yet for any particular psi and phi, the inner product is almost exactly preserved. And we're going to see in a sec that something even stronger is true.
So here it's important that you don't know.
Yeah, so in these calculations, psi and phi are taken to be independent of U. So you can think of that as kind of an avatar for saying that they have simple low complexity, right? I'm going to actually prove that directly in a sec. So just hang on a sec about that. So I wanted to mention, well, time is running out. I just wanted to briefly mention there's an even simpler version of this where if you just take a complete basis, so for now, if we ignore, I'll just ignore little l for a sec. If you just define a holographic map, so this is just kind of a baby version. Okay. So ignoring L for a sec, then I want to, this should be a little r, sorry. If you have a holographic map that just takes the interior right movers in some complete basis, and then just maps them into sort of uniform superpositions of states in the microscopic description, but with phases that are uncorrelated. So if you like, you can, you draw each of these phases independently from the uniform measure on the circle. But again, you only draw it once, and then you stick to it. You don't average, okay? Then you can check that if you compute, okay, what's this? It's 1 over b times the sum over b, e to the I, theta of n b minus theta of n prime b, okay? And what's that? Well, it's equal to 1 if n equals n prime, because then the phases cancel and the sum just cancels that. But then it's order 1 over the square root of b if n is not equal to n prime. Because then this is like a random walk, so this gives a square root of b, but then because of this, it becomes 1 over square root of b. Okay. So this is kind of the essence of what's happening here. So you can just get a surprisingly maybe large number of almost orthogonal states in a Hilbert space, much larger than the dimensionality of the Hilbert space. You do get into trouble if you try to take this to be exponentially bigger than that, because then just kind of by chance, some of these can be big. Okay. So in general, we're gonna be in this regime, but not in the regime where this is large compared to e to the b. What's the? Is this this is the eraser? Okay, let's try. Sorry, what? Oh, the round thing? Oh, I see, okay, all right. Novel. Do you think the cloth is better? Okay, I'll listen to the boss. It's a local knowledge. Okay, so I just want to make a comment about measure concentration. So we showed just a second ago that for any particular psi and phi, their overlap is likely to be preserved, but we could ask for something stronger, right? So claim, so psi, phi is likely preserved for all sub-exponential states. So states of sub-exponential complexity. Actually, in lieu of time, I'm kind of tempted to just assert that and then keep going. So if you want to see the proof of that, which uses measure concentration, then ask me. So then I will jump on to the QES formula. So now let me take a particular state, which I'll call H for Hawking. This is a state in the effective description. What I'll do is I'll have some state where I take the ingoing modes L and I entangle them with some reference system capital L. That's just the usual thing of purifying so that you can keep track of a bunch of states at once. And then following Hawking, I'll imagine that there's some entangled pure state of little r and big R. Okay? And you should think of these as both being sort of highly entangled, maybe almost maximal or even maximal. If it's actually maximal, there's some additional annoyances, but let's think of it as being almost maximal. Then we can let's do a warm-up calculation. So let's compute the second Renyi entropy. So let's compute, on average, e to the minus s2 of, well, let me introduce some other notation. Let me define psi LBR to be the encoded version of this state. So it's V tensor I acting on psi H, V dagger tensor I. So then here I put psi R. Okay, so that's the fundamental description. And I take the encoded version of the Hawking state in the fundamental description, and I look at the reduced state just on the radiation, since for the page curve that's what we want. Let's compute the average of its second Renyi entropy. So there's some nasty formula, which I'll write. This will be the only time I write one of these formulas in detail. Okay. So that's just doing the unitary integrals. What does that really tell us? Okay, it tells us that the second Renyi of the Hawking radiation is equal to the minimum of the second Renyi in the effective description, which is the entropy that Hawking would have computed, But then there's a minimum, and we have to compare that to the logarithm of B, so this is the black hole entropy, plus the second Renyi of L in the infalling state. Okay. And this is exactly what you would expect. Well, okay, I did the calculation here for the second Renyi. The same formula is actually true for any Renyi, and also therefore for the von Neumann entropy as well. I won't show you the calculation. So then, if we compare to the QES calculation, right? So at quote early times, we're here, well, we don't have time yet, but the early times just means that LR is small compared to B. Then, well, there's a log B here, so then this term is going to be the smaller one. And so that's describing the situation where the entanglement wedge of the radiation is like that and the island is not included. That's this term. But then when the black hole is old, meaning that the radiation gets very entropic, then we're supposed to include the island. And that's this term here, right? So you can see now the entropy of the radiation is purified by the R modes in the island, but this one is not purified, so that's still left over, right? Because the left movers here. And then there's this area term from the edge of the QES. But you see here now, though there was no Euclidean gravity, right? I didn't use the QES formula. I just calculated the entropy, and I got the answer that I would have gotten by using the QES formula. Okay.
Question. Did you have to renormalize the wave function when you computed those entropies?
Yeah. Well, that's built in from the square root of P.
No, I mean, because that V, I see.
Yeah, this state has a norm that's very close to 1.
It's close to 1.
Close to 1, yeah.
And
Yeah.
that's
So
sufficient.
so I'm not, to make life simple, I want the holographic map to be linear. So when I act, I get a state that's not quite normalized, but I don't renormalize it. Because if I did, that would be a nonlinear map, and I'd rather not have a nonlinear map.
So then you use a different I mean, maybe this is a
No, the rules are that I'm willing to tolerate exponentially small errors. That's the rules of the game. So I'm not going to work hard to avoid exponentially small errors because we're going to have them no matter what.
And you still use trace row log row with row is.
Oh well, yeah. If you want to,
slightly
So you can use the version where you fix up the norm a little bit, but it'll just affect
won't matter,
exponentially
yeah.
small things. It won't matter. Yeah. Okay. Yeah. So this is the thing I said before, that we can derive the QES result without using the QES formula. Okay. Let me just make 2 comments. So you can also this is also true in the phase model. So if I take this thing with the random phases and I compute again the e to the minus the second Renyi entropy on R, I'll just tell you the answer. It's 1 over b squared, and then there's a sum over n and n prime, b and b prime, dn prime, where, these d's are, you take this chi r to be something like that. Okay, so that's what the d's are. And then there's some phases. Okay, but then this is going to be dominated by the terms in the sum where all these phases cancel. You don't need to worry about exactly what the phases are. They're just some phases, okay? So there's 2 ways for the phases to cancel. They can cancel if n equals n prime, and then this cancels and this cancels, or they can cancel if b equals b prime, in which case this and this cancel, and so that gives you 2 terms. There's a term which is like the sum on n dn squared, and then there's a term which is like 1 over b. Okay, and this term is the second Renyi entropy of the radiation in the effective description. That's Hawking's calculation of the Renyi entropy. And this is the term that comes from the double trumpet if you do the Euclidean calculation. But here there's no double trumpet or anything. We just computed trace of rho squared, and we got this term. Okay. So I'll just say in words and then skip. So you can work out entanglement wedge reconstruction here. So you can use decoupling theorems to figure out, say in the Hawking state, when are observables in the interior reconstructible on the radiation or on the B system, and it works in the way that you want. Okay, so at late times, the information is in the radiation. And like I said before, you can think about that as because this V is not in isometry and there are these null states that when you act with it, it can teleport information out into the radiation, even though the map accesses the identity on the radiation. You can similarly work out a sort of measurement theory where for any observable in the interior, if you want to know like what's the probability that that observable gives some result, you can work out a generalized measurement in the fundamental description, where if you do that, it gives you the same measurement probabilities for outcomes and projects onto the same states. But I won't explain that either. I instead want to draw a picture for the dynamical model, and then I'll be done, since dynamics are important. So let's go on to the dynamical model. It'll just be 5 minutes. Sorry, I'm going a little over. This is easier to explain with pictures than words. So here's the idea. So I'm going to start in the fundamental description. So I have some, so what I'm going to do is I'm going to collapse the shell to make a black hole, and then I'm going to evaporate it. Okay? So the collapsing shell is going to have two parts. There will be some degrees of freedom that I can vary, and then there will be some degrees of freedom that are fixed, okay? If you like, I'm gonna, for now, try to restrict to a fast collapse, right? I don't wanna think about a typical state right away. I wanna think about a star that collapsed or something, right? And so we know that the degrees of freedom in that are less than the full degrees of freedom in the black hole, and so that's, this L naught is like, tells you about the baryons or whatever that collapsed in the shell, and then these are fixed just to remind you that you're not building up a typical state over a long time. So then there will be a unitary, U naught, which implements the collapse, after which we have a bunch of black hole degrees of freedom. Okay. Now, here's how the dynamics are going to work, and it's great that I have colored chalk. So we're just going to do the same procedure over and over again, so I'll just draw it twice. So we have an infalling mode that goes in, because, well, we could drop something into the black hole after we make it, right? We feed that into a big unitary, U1, and then out come two Hawking quanta. Yeah?
I would have thought the infalling mode comes from the fact that the black hole evaporation it produces entropy.
Yeah, that's also related to, that's related to this also, right?
Yeah, but I mean, if you're going to iterate, I mean, isn't it true that we want at every step, we want sort of
You could choose
one in,
not
two
to
out
throw
or something like that?
You could choose not to throw anything in here. I just want to give us the freedom to throw something in. For example, if we want to do the Hayden-Preskel thing where you throw in a diary and see how long it takes.
So you're not trying to model the fact that the Hawking radiation has some order 1 factor larger.
No, I
entropy?
am. I think that's just kind of baked in here, right? This collapse.
No, I would have thought that the psi is the difference between the coarse-grained entropy of the star and that of the initial black hole. Isn't that?
Yeah. Okay. Yeah. Maybe you can also try to interpret this. I mean, this
that's
model
right,
will
yeah.
certainly have that feature. I'm not sure I want to put a finger on exactly whether it's this or this that's responsible for it.
In Pennington and Hayden's paper, that's why I'm saying this.
Yeah.
That's the reason that extra leg is there.
Yeah. Well, I mean, we can say that, but it has the added benefit that I can think about experiments where I drop something in, right? Because I want to talk about these left-moving modes at later times, and those modes fell in at earlier times, so I have to put them somewhere, right? Okay, so, okay, and then we just keep doing this. So I'll draw one more step of it, then there'll be a U2, where, oh, sorry, I got to extend it over a little bit more, where another infaller goes in, and 2 more radiation quanta come out, and then there's some remaining black hole. And then you can see each time I do this process, the black hole, qubits, the white ones, decrease by 1, and so the black hole is evaporating. Okay? And so there will be some final step after which only radiation is left. Okay? So this is clearly unitary, right? We can't argue with this being unitary. Okay, so this is the fundamental description. Okay, but where's the interior? Okay, so now I have to do a slightly annoying thing, which is I have to draw the picture again. I'll try to do it fast. I've gotten pretty good at drawing this picture. This one should go all the way over though. This one can go over a little further. And then there's these red modes coming out. And then some. Okay, so I guess we can put the names. Okay. Now I'm just going to do something which is mathematically trivial, but which I think conceptually is very non-trivial, which is I'm just going to take these red lines here, and I'm going to bend them around. And then that was so much fun that I'm going to bend them around again. Okay, where this can now be thought of as a post-selection, and this is inserting a maximally mixed state. Okay, but so far I've done nothing, right? This is the same thing that it was before. But now we're going to reinterpret it. Actually, I should make these blue. I think is better.
Sorry, are you also multiplying by p or something like that?
Yeah. So when I put in the factors of p such that this equals that.
Okay.
Okay. Yeah. Yeah. Don't ask me what they are off the top of my head. So now here's the key thing. So this here, I'm going to call L. This here, I'm going to call little r. This here, I'm going to call big R. This here, I'm going to call B. And this here, I'm going to call R. And this here, I'm going to call 0p. And now if you stare at this picture, what is happening? I've got an initial state here of some infalling modes, which we could have purified them like we did before in the Hawking state, but here I didn't. But if you want to, we can purify them. We've got the left-moving modes inside. We've got the right-moving modes inside. We've got the Hawking radiation here. And if you just look above this line, what are we doing? We're acting with a non-isometric map on L and R, and here's psi naught F here, right? And then we're acting with the identity on the radiation, okay? And so we've just recast the unitary dynamics of the fundamental description into a picture which looks exactly like the picture we were talking about before, where you have this non-isometric encoding that takes the interior, maps it into B, takes the radiation, maps it into R, but then because of the post-selection, if you go for long enough, then the information makes it out into the radiation, okay? And so I claim in this model, well, I erased it, but I claim this has all 3 of the features that Hawking talked about. Yeah?
It seems that in that picture, L and R are treated differently from one another, but in the space-time picture, they're both in the interior. So how do you
Yeah. So we've been working in this crude approximation where they're not interacting with each other, which, as you know, for this kind of post-selection things, is tempting. It makes things simpler. You're right. I think that there does need to be some interactions between L and R that are included, which are not included in this picture.
No, I didn't care about the interaction.
Yeah.
I see that in
Yeah.
and then there's a projection that happens on
Oh, yeah. Oh, so what's bothering you is that the unitary doesn't also act here, right?
effectively.
Yeah, but right, but it turns out not to matter so much because there's this post selection here, right? So if you want to, you can stick a unitary here and then just move it over there, right? And the fact that this is maximally mixed kind of effectively implements the unitary. It's by the way, I should say it's actually good that there isn't a whole big unitary here, because that would actually give you the wrong page curve, because of this non-adiabatic nature of the radiation. So it's actually kind of important that once the modes get out of the black hole, they're sort of not affected anymore. But the interactions do worry me a little bit more, right? I mean, there should be some, these should get mixed up a little bit by interactions. I feel like that should be treatable perturbatively, but it'll probably mean that this exact equivalence is too much to ask for. That probably there will be some approximate thing that's true. Yeah.
So for L, this could be a star in a mixed state, which I could model by having L entangled with some external reference
Of course,
system.
yeah, just entangle it with some reference system.
But if you did the same to R, then you couldn't write down the other.
Yeah, good. So this picture has a preferred state for little r and big R, right? But if I just take the map up here, this defines the map, and I can feed whatever into it I want. I don't have to feed this state.
That's what I meant in the beginning by
Yeah.
saying that you're ultimately committing to a certain code subspace. And what's happening with these additional degrees of freedom that you've introduced is they're basically frozen.
No, because there are several reasons why not, right? So first of all, this was, I just drew this picture to motivate the map, okay? But once I have the map, I can just study the map as I was doing before, and I can see that it has the properties I said, approximately.
But you
preserving
can't
the inner
include
product.
little r in the code subspace. If
Sorry,
you
what?
did- to
No.
include-
So the code subspace for me is anything that, it doesn't have to be this fed in. The code subspace is you can feed in whatever you want here. And in particular, let me emphasize that although I didn't have time to explain it, you're allowed to do measurements in our rules, right? So you're allowed to do something like evolve for a while and then do a complete projective measurement on the radiation and then evolve for some more. That's allowed and everything works in the way you want.
But do you agree that if little r was entangled and purified by an external reference system, that you could not push the state out to big R? And with this,
Yeah, but that's correct. Yeah, so if you do right, but what I just said is like that, right? So do a complete projective measurement on the radiation, okay? Nothing exponentially complex, just, measure each spin in the z basis or something, right? So once you do that, the radiation is in a pure state. And so it must be that after you did that, even if the information was in the radiation before, it's not now. And that's a true feature of this map. That's a true feature of this map.
I'm discussing the asymmetry between little l and little r, where little l could have been entangled and purified by an external reference system, but you couldn't start by imposing that on little r.
No, well, how should I say, right? I mean, there's a, you can do that, right? You can choose to entangle little r with something other than big R. Okay, that's fine, right? This map can act on states like that, and it'll have the properties I said. Okay? It's just that those aren't the states that I'm trying to do the thing Hawking wanted, right? I want to collapse a black hole and then evolve it, okay? And if I do that, then of course I'm going to get this state in the effective description, right? But I'm not saying that that's the only state that makes sense, right? Like in particular, I want to say the vacuum is not frozen for us, right? Like you can take the Hawking state, right? This is the Hawking state. You can act with the unitary here and then pass that through the map, and you'll see, that something is different if you do that. And it's unique. I didn't emphasize this enough because I didn't talk about measurements, but there's a very important theorem for the self-consistency of this, which is that if psi and phi are sub-exponential, then V tensor I acting on psi is approximately equal to V, where approximately means to exponential precision, is approximately equal to V tensor I acting on phi, if and only if psi is approximately equal to phi, okay? So you're not going to have a situation, so like in what you said, right, like if I take the Hawking state and I act with the unitary that messes up some modes okay? That'll give me two states that are not equal in the effective description, right? In the effective description, they'll clearly be different. And this map has the property that after I act with it, they'll still be different. So if you like, although this map is not an isometry, it is invertible on the set of sub-exponential states. And so if we're willing to satisfy ourselves with that, it seems we can get most of what we want. I mean, yeah, I'm basically done here. Let me see. Okay, let me just make two very brief comments, okay? So this picture looks a lot like final state, right? So let me just comment on that for a sec, right? So if you run this evolution all the way so that the black hole is gone, okay, and then you do this, it's exactly final state, okay? So this mechanism of, you post-select, and then that teleports the information out is the same as final state, okay? But there are two very important differences with final state. The first is that I'm not interpreting the post-selection as happening in the effective description. It's part of the holographic map. If you just look at the effective description, it's perfectly unitary in conventional quantum mechanics. You just, what it does is it just keeps adding more and more EPR pairs here, just like the bulk effective field theory would say. And then at whatever time you want to do measurements, then you push it through the holographic map at that time, okay? And so because whereas in the final state proposal, there's no holography, right? You're just trying to do everything in the bulk, okay? So the advantage of doing things this way is that there aren't any violations of causality. If you want to do a measurement at time t, you evolve to time t, and then you do a conventional measurement. So you never have this thing that you have in final state, which is that the results of earlier measurements depend on whether or not you did later measurements, okay?
Measurements which are sub-exponential in complexity, then you wouldn't have any problem?
Yeah, maybe, right? I mean, it's possible. It's possible. Yeah, yeah. But I think,
Somehow the same
I mean,
type of
here you can do things that are exponentially complex here, and you also won't violate causality. You'll have some other problems, right? But you won't violate causality. Yeah. They're clearly related. I don't want to say they're not related. It's just I think it's different because here I'm really trying to do holography. I'm not trying to come up with a bulk description of how information gets out, okay? And so, and that, maybe let me close on that this V, right, is not a thing that lives in the effective theory. It's a thing that tells you how the effective theory is mapped into some deeper description of what's going on. So if we knew, something like non-perturbative string theory and the bulk or something like that, the idea is that from that you could derive the V. So somehow the non-perturbative string theory, I would guess, is unitarily or isometrically equivalent to the fundamental description. But when you want to have this effective description in terms of low energy modes, then you have this non-isometric map that you ideally should be able to derive from the fundamental description. I think in ADS-CFT, in principle, you could even do it, although we didn't try. But you would have to use some consistency arguments, so it would not be as satisfying as really just like starting with non-perturbative string theory and not having to use consistency. Okay, so I should stop. I'm over time.
Thanks a lot for the talk. I have a question about the complexity that you didn't really talk about.
Yeah.
But concretely, if you, for example, make this statement that is on the lower blackboard on the left, on the top part, in this little box.
Oh,
like,
yeah.
Yeah. Could one say that actually this should be true for any sufficiently small set of states, however you define it?
That's
and
correct, yes,
therefore
that's
in
correct.
particular
Absolutely,
for-
yeah. And so I just picked the sub, yeah, exactly. So for you, I can just say, right, you use the union bound, so you use some version, it's not, you can't use Levy's lemma, but something like it.
So it's basically independent of how precisely you define complexity.
Yeah, you just need to pick a set of states which is small enough, and sub-exponential turns out to be small enough, yeah.